All right. Hello, everyone. So today we're going to start the second half of the chapter 4 stuff that I've broken this into. So it's 4.3, the acid-base reaction. Uh, you'll find the notes. Uh, you'll find the notes posted in your Google Classroom. Okay. Uh, these are in PDF form. These are ones I was talking to you guys about that are hacked together from some of the information I had. So, all right. Acid-base reactions. Acids are substances that are able to ionize an aqueous solution to form a hydrogen ion. Ionization occurs when a neutral substance forms ions in solution. So you get an example, acetic acid. We've already talked about this previously. When it ionizes, when you put it in water, you get H plus and you get C2H3O2, right? Okay. So this is a hydrogen ion. It says since H plus is a naked proton, we refer to acids as proton donors and bases as proton acceptors. So just to kind of explain this, so if we have like this, like 1/1 hydrogen, a regular hydrogen atom, that has one proton, one electron, and 0 neutrons. Okay, if we have this, the plus 1, okay, that's still one proton. One proton. It is now, the plus 1 tells us we lost an electron, so it'd be no electrons and still no neutrons. So I just wrote this just to show you when it says it's a naked proton, what that basically means is a hydrogen ion is just a proton. It's the exact same thing as just a proton, okay? So things that donate a hydrogen ion in solution, acids would be proton donors because they're giving up hydrogen ions in solution. Bases in solution are proton acceptors. They're going to actually take the proton or the hydrogen ion. Okay, so they list some common acids here: HCl, HNO3, vinegar, vitamin C. Vinegar, acetic acid is vinegar. So this part here, acids that ionize to form one H plus ion are called monoprotic acids, and acids that ionize to form two H plus ions are called diprotic. So what does that mean? Well, something like HCl is going to produce H plus, right? Like one H plus and one Cl minus. So it just produces one of the H plus here. A diprotic would be something like, let's say H2CO3, carbonic acid. Okay. Carbonic acid is going to actually produce two hydrogen ions and one carbonate ion. So this would be diprotic, this would be monoprotic. Okay. All right, bases. Bases are substances that accept or react with the hydrogen ions formed by acids. Thus, they're called proton acceptor. So hydroxide ions, OH, react with the hydrogen ions to form water. Okay, so you've got a hydrogen aqueous plus the hydroxide ion to form water, H2O. This is actually what we refer to a lot of times as a neutralization reaction, which we'll talk about a little more later. Okay. All right. So they give us some common bases. You should memorize that ammonia is a common base because that's not one that has a hydroxide on it. We usually know that most things that have a hydroxide are common bases, but ammonia is not like that. So compounds that do not contain, well, what I just talked about, do not contain hydroxide can also be bases. You get a proton transfer to NH3, which is a weak base, from water, a weak acid. So water would give off a hydrogen ion, and that would transfer to ammonia. Okay. So what actually would occur is the water gives up a hydrogen, right? And then the ammonia. So if you look down here, here's the reaction. NH3 aqueous, the ammonia, is reacting with water. The water gives up a hydrogen to the NH3. So this becomes now an ion, actually, NH4. This becomes ammonium ion. And then the water, because it lost a hydrogen, is now a hydroxide. So in the end, you have a hydroxide ion in the water, which is normally what we think of as something as being a base. We normally think a base is something that kicks off a hydroxide ion. But in this case, it didn't actually give off a hydroxide. It created one when it reacted with water. Okay. All right. Strong and weak acids and bases. So this is some of the stuff that I actually that we skipped from the last chapter, the strong and weak acids and bases. But you do have that help sheet. Actually, I'm going to go grab that real quick and pull that up. Okay, so it's the solubility rules tables, the help sheet that I gave you guys. It also has the common strong acids and bases tables, okay, along with the electrolyte table down here. So we're going to be still using this. Okay. If you don't have one of these, I'm going to post it in the resources section of the classroom. Okay. All right. So strong acids and strong bases are strong electrolytes. In other words, they are completely ionized in solution. Okay. All right. Weak acids and weak bases are weak electrolytes. They are only partially ionized in an aqueous solution. So we talked about strong versus weak electrolytes, right? Strong electrolytes are substances that completely ionize or break up. Weak electrolytes are things that only partially ionize. Some of it stays together as the compound, and some of it breaks apart. Okay. Strong bases include group 1A metal hydroxides. So when it's talking group 1A metal hydroxides, what that's referring to is anything that is in group 1A here, hydrogen, or well, it won't be hydrogen, that's water, but lithium, sodium, potassium, these. If these are combined with a hydroxide, those will be strong bases. Calcium hydroxide, barium hydroxide, strontium hydroxide, a couple that are in the second column. Some strong acids, hydrochloric, hydrobromic, hydroiodic. Okay. This list here is your strong acids and bases table. So I've listed the strong acids, I've listed the strong bases. Okay. All right. They're showing ionization of a strong acid here. We've already done these. okay? Weak acids and weak bases are weak electrolytes, only partially ionized. Hydrofluoric aqueous is a weak acid. Most acids are weak acids. So they're showing you ionization of a weak acid here, where you have hydrofluoric. The only real difference, remember, in showing this is that you've got the double arrow going both ways because some of them remain as the compound together and some of it splits and ionizes. All right. Now, how do you know if it's a strong acid or strong base or a weak acid or a weak base? Well, that's this table. Essentially, if you have an acid or base, you look it up here. If it's on this, if it's a strong acid or a strong base, it'll be listed on here. If it is an acid or a base and it's not on this table, for what we're doing, you can assume it is weak. So if you know it's an acid, but it's not listed on this table, you'll say it's a weak acid. If you know it's a base, but it's not listed on this table, you'll say it's a weak base. Okay? All right. Next section. Identifying strong and weak electrolytes. Compounds can be classified as strong electrolytes, weak electrolytes, or non-electrolytes. Okay? And I already sort of went through this with you guys, if you recall. Hold on, let me. Okay, so I just pulled this up. Oops, hold on. Yeah, I know it's being recorded. Okay, so there we go. Okay, strong electrolytes, all ionize in solution. Weak electrolytes, some stay as a molecule, but some ionize, both. And then non-electrolytes completely stay as molecules. There's no ionization at all. All right, so we've already kind of talked through that. I will post that image of those notes that we talked about before as well with this stuff, so you'll have it. Okay. So they basically go through stuff here. How do you classify them? Strong electrolytes are soluble ionic compounds are strong electrolytes, so anything that can be dissolved. Molecular compounds that are strong acids are strong electrolytes. So what I've done is this electrolyte table on this help sheet again is here. If it is a soluble, so remember from this, if it's a soluble ionic compound, so that would be here or here. If it's a soluble ionic compound, then it will be a strong electrolyte. Okay. If it's an insoluble compound, it won't be an electrolyte because remember, insoluble means it doesn't, it won't be aqueous. It won't dissolve and ionize. So if it doesn't dissolve and ionize, it can't be an electrolyte. Okay. So strong electrolyte, ionic. Okay. Now I didn't put any ionic under non-electrolyte, which would be the insoluble ones, because I'm trying to kind of keep it simple here. So if it's ionic, strong electrolyte. Molecular, right, like covalent. Okay, if it's molecular, if it's a strong acid or a strong base, it will be a strong electrolyte. So you would look here, if it's molecular, if it's a strong acid or a strong base, it's going to be a strong electrolyte. If it's an acid or a base, but it's not strong, it'll be a weak electrolyte. If it's molecular and it's not an acid or a base, then it's going to be a non-electrolyte. Okay, so for example, the sugar, hold on, go back to this. Sugar is a non-electrolyte. Okay, because it's not an acid or a base and it's a molecule. It's molecular. Okay. There are some you might have to be a little careful of. So like, because we're used to things with hydroxide at the end of them being being bases. There are some though you have to kind of watch, like this. Okay, this is a molecule. It's a molecule. Um, it's part of a category of alcohols. But if you look at it, it has it looks like it has a hydroxide on it, right? So people sometimes think, oh, well, that's a base. Okay. But it doesn't, uh, since it doesn't have a metal cation, it's not a base. Okay, so this would be a molecule. This would be a non-electrolyte. All right, makes sense? Okay, so I'm going to stop this video here because this will be like listed under the acid-base reaction with the electrolyte stuff. Okay, and then I'm going to do a second video, so they're kind of split up for you on the neutralization reaction with the salts and the acid-base reaction with the gas formation stuff. Right? All right.